I'm going to speak today about Markov chain. I'm speaking about it in the context of reinforcement learning. Reinforcement learning is a context in which we have we have a decision maker who is making decision over time, and the environment gives that decision maker rewards. Once the decision, if the decision maker is making the decisions in a stationary manner, which means every time, regardless of the past, okay, and the environment takes its next step, moves the system into its next step, regardless of the past. Once the policy of the decision maker is made, we get a Markov chain. Okay, so that's why we're going to speak today about the Markov chains and just start to set up the basis of our understanding of the structure of Markov chains and so on, so we can use that for reinforcement learning. That's the objective of what we're going to do today. Okay, so have a look here. There's a stochastic process, which means we have a random variable that takes values over time. Okay, and the key Markovian assumption is that the probability that we take some state in stage n+1 is not dependent on the history. So basically, it only depends on the current state. So this conditional probability simplifies to this one. So we're only interested in the current state in order to determine the next state. That's the Markovian assumption. Okay? And once you have a Markovian assumption on a stochastic process, you get a very simple algebraic behavior of the process, which I'm going to outline quickly now. So let's use the following notation. We'll call that probability Qij, which basically means the probability of moving from state I to state j. It's always, we'll assume it's independent of time. Okay, so regardless of any time in any stage in the process, that's going to be the probability that we move from I to j. And we'll have a matrix which we call the transition matrix. Basically tells us what's the probability we move from I to j, and we'll have a finite state of the Markovian process. So all of these are simplifying assumptions, Markovian simplifying assumptions, but with that context, we'll be able to do a lot of things with reinforcement learning. So that's a good enough context to start with. And let's see the algebraic structure. So just the thing I want to ask is, what's the probability I get in 2 steps to j from I, not in 1 step? Okay? So if I expand it according to the law of probabilities, I first get this summation. What does it mean? Well, I can go to any of the states from I, any of the state k, and then so from state I go to state k in stage n+1, and then from state k I go to state j. So that's going from state I to state j in 2 steps. Okay? Now the interesting thing is that the Markovian assumptions kicks in, and this is, we can ignore it basically. That's the Markovian assumption, and we basically get that, which is essentially the ij entry in the product of the matrix Q by itself. So if you take the matrix and multiply it, the ij entry will be what's the probability of getting from I to j in 2 steps, and so on for any power of the matrix. So that's basically the basic underlying algebraic structure that we'll be able to utilize later on when we use when we want to study reinforcement learning. Thank you.